So what we're hoping to explore with Cannini is using hyperspectral data to measure water quality, health, and species of coral and seagrass at a much larger scale. So we're not now talking about a particular island here and there, but we're talking about the entire barrier reef or Ningaloo, for example. The other example we have here is the heat waves. So we're using, Cannini has a very special thermal infrared part of its sensor, and we use that to measure heat waves in Adelaide. And that's really to compare whether the heat waves are concentrating in urban areas and what the natural environment does to help alleviate that. And the last little example I've got from Cannini is the eco-mapping. So the hyperspectral data can be used to better understand the vegetation communities. And essentially what that means, it has potential to discriminate and map native species versus invasive species. And that's quite important, particularly when we come to rehabilitation of land, but also things like mapping the burn scars from bushfires and understanding how that vegetation is regrowing and the health of that vegetation. Okay, moving on to the second of three examples out of the CRC, so CHORUS. So what CHORUS stands for is Compact Hybrid Optical RF User Segment. And once again, this is a great example of a collaborative SmartSat project. So CHORUS, as our project, has gone through 2 iterations of funding cycles. And we've actually developed a CHORUS terminal. For those that have been to a couple of past conferences, you would have seen it. So we actually have a physical prototype of the ground segment. And basically what this does is it combines RF and optical communication capabilities, and it builds on some amazing background IP out of industry, and most importantly, it actually delivers, or is aimed to deliver, a capability that defence needs. So again, it's that end user pull. Now, most recently we would have heard of the last couple of days the announcement of the Optus Swift mission. So what we've developed at the CRC so far is this ground segment. What's missing is the space segment. And we're very proud to be supporting that Swift mission by developing the space segment, so the partner to this ground station. And we're doing that through partnership with the University of South Australia, who will be developing that space component. So, like I said, it's an Optus-led project, but it's clearly got that industry need, it's got that end user pool, and at the end of the day, defence and commercial satellite communications can really benefit from this. Okay, almost there. All right, last example I want to give out of the CRC before we let the panel come up is our Ascend to LEO project. And this successfully demonstrated a push-to-talk capabilities from safety from space. And what we did is we put that waveform, which is used for mobile military communications, on board a Fleet Space Centauri 4 satellite. And this project was quite phenomenal. Over the period of just 12 months, we built 5 variations of a waveform using the Safety from Space Beagle framework. And we demonstrated it on orbit, but we also reprogrammed the spacecraft whilst it was in orbit. And that's an incredibly advanced thing to do. And this was demonstrated to defence. So again, real impact coming from baseline R&D with that industry pull. So as we move forward and look at the longer term, as you would have heard yesterday from Andy, the CRC, it's a 7-year program. We're in our 6th year, but we certainly have ambitions for what the next generation of the SmartSat entity will look like. And we're really encouraging to have continued support across the sector from government, from investors, into what the next phase or the next 4 years of what that looks like for the Australian space research and development sector, whilst encouraging that to be implemented for impact. Okay, so I'll finish up there. What I'll do now is I'll invite our speakers to come up one at a time, and then once all the speakers have had their chance to present their work, then we'll all come back up on stage again for Q&A. Okay, so first one, we've got Anne. So Dr. Anne Bettens has a PhD in vision-based navigation in space and is one of our SmartSat CRC PhDs. She's the CEO and co-founder of Deneb Space, which is an Australian startup aiming to automate satellite manoeuvring in space. So, all yours.
Okay, good morning everybody. So yes, I'm Anne Bettens. So I've been involved in a lot of different research projects, both globally but also here in Australia. And I'd intended this slide to highlight some of those R&D research projects, but I think I've actually just highlighted that I'm a bit of a nerd, so we've got that here. But this kind of gives a bit of context as to some of the stuff we're doing at Deneb Space, but also having that deep roots in research and development, and then the impact that we can generate from that. So you may or may not already be aware, but there's quite a high failure rate of satellites in low Earth orbit. We've also heard a lot from the conference over the last few days, but also just in general from industry, that there's a lot of things orbiting in space. So if we're combining seeing this significant increase in the number of satellites going to orbit with this lack of reliability in the way that they're operating, we're coming across some pretty big problems. Now, the reason I'm starting off by highlighting the problem here is that a lot of the time we see research and development for the sake of it, but I think anchoring it in a significant problem that impacts a whole industry is really crucial to the way that we actually make meaningful impact in industry. So the way that we intend to do this with Deneb Space is basically coupling attitude determination and control hardware with attitude determination and control software, and really deeply integrating that on a systems level. So for those that perhaps aren't so technical and haven't done that kind of nerd work that I introduced on my first slide, attitude determination and control is making sure the satellite's facing the right way and staying on track and doing what it should be doing so it can do the successful mission outcomes. And for example, we saw a fantastic, those images from Cannard. It's because the satellite's facing the right way and able to take those images. So what we've done is coupling hardware, software, integrating it together really well with some more advanced AI pose estimation algorithms as well. Integrating all this together, we've got this really sweet spot in a way in which we can enable an autonomous satellite to have this fantastic capability. So we're very excited because we have flight-proven hardware, so we've got two pieces of tech orbiting in space at the moment. But really our mission is to make satellites smarter, agile, and far more maneuverable. And this is particularly interesting for satellite operations. If we want to have stable satellites, we want to be detumbling so that they're very, once they're deployed, they're very stable and they're able to start doing what they should be doing essentially. But this really comes into, if we start looking at collision avoidance, we saw that kind of significant number of satellites in space at the moment. We really need to have this reliable operations system. Additionally, as the industry is starting to look at rendezvous and close proximity for things like in-orbit servicing, debris removal, we really need to have the smarts on board of the systems of the satellites in space. So some examples in which the way that we do this is we have our EMAG, as I said, we've got that payload up there in space at the moment. We're really excited about this because compared to current competitors in the market, this has 10 times the amount of rotational torque, and it only uses 50% of the power. Sorry, excuse me. So this is pretty exciting for a satellite because it really gives it the oomph to be able to be that maneuverable, be that really maneuverable and agile satellite platform that doesn't currently exist in the market. So coupling that hardware with our intelligent software really is a step change in the way that we see that satellites will be operating in space. So this is pretty exciting as we kind of plan to do this end-to-end satellite autonomy. So as I said, a lot of this has been based on research and development, and really taking this to flight-ready innovation has meant that we've had 2 successful satellites launched as part of the Quava and Waratah seed missions. But really a key learning for the Deneb Space team, because we were involved in supporting the operations and the commissioning of the satellites, we've actually discovered a lot of new capability that doesn't exist in the industry at the moment. So having the ability to instantly detumble a satellite, sometimes it takes industry 3 to 6 months to do that detumbling commissioning. You can imagine in that time, if your satellite's spinning around, you're not able to communicate with it, it's not able to do the operations that it should be doing. But imagine if you can do that instantly. That's a huge de-risking for the industry, but also fantastic new opportunities there of, imagine if we can just squeeze a little bit more out of these satellites in orbit. As I said, we have this EMAG flight heritage, so it's proven in space, but this also allows us to get a high commercial readiness level. So we've taken this tech, this research and development, got it in space, put it through its paces, and now we're selling it to customers. So really taking it from that low TRL readiness level to a commercial product in the market. The really exciting thing as well about having these kind of learnings and being really deeply involved in the research and development means that we intentionally design with scalability and interoperability in all of our products, and that's sort of how we scale as a business, going more towards this satellite autonomy. So if we sort of start to look at this roadmap of where we are and where we're going, having this deep roots in this research development, this knowledge, this really technical expertise in our co-founding team means that we've got this flight heritage, we've had these learnings, we've discovered these new capabilities that we've unlocked, and we really do have a solid roadmap moving forward towards autonomy, both on a technical standpoint, but also really validating it in the market as well. So we've got some pretty exciting opportunities coming up there. So just kind of, I guess, taking a little step back and giving some context and maybe framing for the panel a little bit later on. Really at Deneb Space, one thing that we do is focus on building this national capability, but with global reach. And the way in which we do this is through really deep collaboration. And what I mean by deep collaboration is really integrating with either other industry partners, researchers, to do things like in-orbit demonstrations, looking at our attitude, determination and control subsystems and how they integrate into other systems and other platforms. As well, using vision-based AI, integrating this into a system. So using AI is kind of a bit of a taboo topic sometimes in the space industry. It can be a little bit conservative, but if we're integrating it in a really meaningful technical way, we really see the path forward here. Additionally, making space-based decisions in orbit is really, really crucial to this as well. So being deeply ingrained in this research and development, but also in this meaningful collaboration and working together really closely is really essential. And kind of, as I've already touched on, so having an engineering approach to that AI in space. So not just doing AI because it's cool and it's a buzzword, but really having an engineering need for it. And then this is where Deneb Space really leads to this sovereign autonomy for Australian missions in the future. So thank you very much for listening to my presentation and look forward to answering some of your questions on the panel.
Almost forgot to come up, I was enjoying that too much. Okay, so our next presenter is Dr. Kimberley Clayfield. She's the Space Research Program Director at the CSIRO, which is Australia's national science agency. Kim has led the CSIRO space research activities since 2018. She's the former chair of the Engineers Australia's National Committee on Space Engineering, a current member of the Australian Academy of Sciences National Committee for Space Science, and was recently awarded the 2025 Australian Female Leader of the Year. Kim.
Thank you. Good morning, everybody. First of all, I would like to acknowledge the Kaurna people on whose lands we meet today and pay my respects to their elders past and present. So, as Sarah said, CSIRO is Australia's national science agency. Our primary functions are to carry out scientific research to benefit Australian industry and the community, and to contribute to the achievement of national objectives. We work across a very broad range of areas, from environment and agriculture to energy, health, minerals and manufacturing, and of course space. So from developing polymer banknotes to the CSIRO Total Wellbeing Diet and AeroGuard, our organisation is all about R&D for impact. Space is a field that is rich with discovery and new science, but it's also fundamental to industry, our national security, and critical infrastructure like weather and GPS satellites that we rely on every day. Having the capability to leverage the space domain is key to our future prosperity, and we've heard a lot of that already here yesterday and today. CSIRO's program of space-related R&D focuses on the use of the space domain from three key angles. So the first is enabling the use of satellite-derived Earth observation data for the benefit of Australia and the globe. For example, by improving bushfire risk reduction nationally, or supporting climate innovation or food security. And CSIRO has a very well-established capability, particularly in advanced data analytics and applications development for Earth observation. The second facet of our space research is looking at how we can use existing radio astronomy research facilities to better understand and characterise the near-Earth space environment, that is, the region between the Earth and the Moon. Understanding the behaviour of objects in orbit, including the way that the space environment interacts with them, is a key part of optimising our use of space. And third, we leverage strengths across the full breadth of CSIRO's expertise, from environmental science to manufacturing, from robotics to life sciences, and we collaborate with Australian and international partners in space science and exploration to help grow commercial opportunities and to grow our understanding of the solar system. CSIRO occupies a unique role in the Australian space ecosystem. You're probably aware CSIRO operates space-related research facilities which are largely unique in their capabilities nationally and often in the Southern Hemisphere or even globally. These include the Novosar-1 Satellite National Facility and the Australia Telescope National Facility. Our space systems engineering and scientific and technical capabilities enable us to translate science goals into instrument specifications and provide input into the design and development of Australian and international space missions that will benefit Australia. And one example of this is a recent joint study that we undertook with NASA JPL to incorporate Australian water quality science needs into the design of a JPL water quality monitoring satellite. We have unique national capabilities in novel satellite data types like synthetic aperture radar and in large-scale data analytics. And we leverage the world-class application science that exists across CSIRO to deliver outcomes, addressing challenges ranging from how to predict and detect harmful algal blooms from space to how to enable remote exploration of the Moon. But we don't work in isolation. Collaboration with Australian and international research, government and industry partners is essential to maximising our impact from the space domain. International partnerships in particular are critical to ensuring access to the satellite data we need for our science and for giving us the opportunity to be part of space missions at scale and achieve global impact with our research. So now I'll just touch on a few of our research projects. First is CyanoSense. CyanoSense is a compact hyperspectral imager that CSIRO is developing with the goal of being able to detect cyanobacteria or blue-green algae in inland and coastal waters from space. It's being developed by the CSIRO Space Optics team here in Adelaide. CyanoSense 1, our initial technology demonstrator, was launched in 2023 on board an Australian Skycraft satellite. CyanoSense 2, which is an upgraded instrument and science demonstrator, was just launched a couple of weeks ago on Gilmour Space's ALARASat bus as part of the on Transporter 14 as part of Gilmour's MMS-1 mission. And so in the red circle here, you can just see MMS-1 separating from Transporter 14. This team also recently co-designed a next-generation CyanoSense instrument with SSTL, and our team has gone through an intensive knowledge transfer effort to uplift their capabilities. Our Space Optics team develops advanced optical payloads for satellite Earth observation but also drone and stratospheric balloon missions, with the aim of delivering outcomes in environmental monitoring, agriculture and disaster resilience. The team works very closely with Australian industry, from component suppliers and integrators right through to end users, to develop technology that is scalable and that is manufacturable in Australia. Several years ago, CSIRO, in partnership with SmartSat CRC, established the AquaWatch Australia program with the goal of establishing a national water quality monitoring and forecasting system to safeguard freshwater and coastal resources. AquaWatch integrates in situ sensors and satellite data with advanced data analytics and modelling capabilities to transform that raw data into insights for the end user. AquaWatch, which is still under development, will initially use existing Earth observation data from international satellites, but the goal is to eventually also be able to include data from bespoke Australian-designed satellites, which are optimised for Australian conditions and needs. And so the CyanoSense instrument is one of the steps towards developing Australian technology to support water quality monitoring from space. The ultimate goal of AquaWatch is to support water managers to monitor natural events like toxic algal blooms, the contamination of drinking water and excess runoff from irrigation, and help increase the resilience of rural and regional communities that depend on water for agriculture and improve environmental outcomes. We're currently operating a number of pilot sites across Australia and internationally, focusing on different areas of application, including mangroves, drinking water supply, salmon aquaculture, and desalination. The pilot sites include research, academic, and commercial partners, with a strong focus on work with local users, governments, and Indigenous community. And we're aiming to have a demonstrator system functioning by the end of 2026. We're leveraging our capabilities in robotics, mining and autonomy to develop technologies that support the exploration of space. And we're achieving international impact through our research and industry partners. Our multi-resolution 3D scanner, which you can see here, began operations in the Kibo module of the International Space Station in August of last year, on board NASA's Astrobee free-flying robot. And if you look closely, you'll see two round lenses that look like eyes on the top. That's the direction the imager is facing there. So as it flies around, it's building up a high-quality 3D map of the station, which supports inventory management and can also support the astronauts as they go about their tasks. The payload was developed by a CSIRO team in partnership with Boeing, and also with the support of the ISS National Laboratory and the NASA Ames Research Centre. In addition to interior spacecraft mapping, this scanning technology also has the potential for monitoring external spacecraft surfaces, for example, to conduct structural monitoring and damage detection. And as you'll see, this scanning technology also has application to surface activities, so navigation, mapping and hazard avoidance for rovers. Last year, we partnered with DLR, the German aerospace agency, to demonstrate our autonomous navigation and mapping capability on DLR's Scout lunar rover, which is designed to test technologies that will support robotic exploration of lava tubes on the moon. And the Scout rover is the one on the left there. Looks a bit like a spider. This demonstration was carried out in lava tubes in the Canary Islands last year. It was the first deployment of the Scout rover in a lava tube, and it successfully performed autonomous mapping and exploration of a previously unmapped lava tube section using CSIRO technology. So this partnership will hopefully lead to future science impact through exploration and understanding of the solar system, and it has also led directly to industry impact. We recently worked with US company Intuitive Machines, equipping their lunar terrain vehicle, Moon Racer, with our autonomous navigation and mapping technology. In a demonstration in May this year at the NASA Johnson Rockyard, which you can see in the video on the right, Moonracer showed its capability to operate entirely autonomously as it navigated that field. So these three projects I've shown you are examples of how we're developing autonomous navigation solutions for extreme environments. And of course, this technology has many other potential applications too. And while we're talking about exploration, I also wanted to note that CSIRO has an in situ resource utilisation, or ISRU, lunar testbed facility in Brisbane for testing rovers and other technology that's destined for the moon. And this can be used not only by our researchers, but also by external research and industry users. And our ISRU team is also investigating technologies that will enable greater exploration of the moon and Mars. One shown here is a new technology for resource characterisation in the lunar environment. The little grey box on the back of the rover there is our novel mini X-ray fluorescence, or XRF device. It only weighs 500 grams and it can be integrated into an ISRU pilot plant or an exploration rover, for example. CSIRO also has a long history in many terrestrial industries, including defence, aviation and mining, where we identify future technology gaps and develop capability and IP that industry can exploit in the future for commercial impact. Two examples of challenges that we know the space ecosystem is facing right now are lightweight and scalable power generation and lightweight shielding materials to reduce the effects of radiation on spacecraft electronics. We're carrying out R&D on printable perovskite solar cell technology for space applications. These solar cells are intended to be cheaper, lighter, and of a higher specific power than current satellite solar cells. And they're also incredibly flexible, which means they can be rolled up for launch and then deployed in space. A sample module went into space in March of last year on Space Machines Company's very first satellite. So we're currently focusing on improving the geometric power density and stability of the cells using the recently commissioned pilot scale printer at CSIRO, shown in the bottom left here. And we're interested in collaborating with industry on in-space demonstration of how our cells could integrate into a solar panel solution. We're also carrying out R&D on specialised metal matrix composite radiation shielding materials. Some of our materials were used on Curtin University's BINAR 2 and 3 satellites, and Spiral Blue's Edge Computing payload on the Waratah Seed mission, all launched in August of last year. So these opportunities enabled us to increase the TRL of this material and demonstrate that it could meet the requirements of launch. We haven't been able to verify the performance of the material in space because of the failure of satellite downlinks, but our ground tests have demonstrated 10 times greater shielding effectiveness in terms of total ionising dose compared to an aluminium shield of the same thickness. So we'd love to talk to any companies who might like some sample radiation enclosure panels at no cost if they're able to deploy these in space and provide some on-orbit data on the performance of the materials. So finally, I just wanted to highlight that there are many routes to partnering with CSIRO to help solve your R&D challenges for space. Some of them are, for instance, using us as a research consultancy or co-investing on R&D projects with us. We do have several long-term strategic research alliances with large companies, for example, with Boeing. We have facilities and laboratories that are available for external use. Importantly, a lot of the technologies that we are developing can be licensed for commercial use. If you're from a university, we do also work closely with universities, and for example, we can co-supervise PhD students as well. And we do offer some programs within CSIRO specifically targeted at helping universities and SMEs to accelerate their R&D. The On Prime and On Accelerate programs are examples of that. and there are a number of other programs through our SME Connect facility. And I also wanted to touch on the fact that we do have many international relationships. We work with many international companies and government agencies, and that's also something that we're able to leverage for our own local Australian partners as well. Thank you very much.
Had no idea you guys did AeroGuard. Okay, so for our third speaker, I'd like to introduce Dr. Seb Ng, the Position, Navigation and Timing, or PNT as we all like to refer to, Program Lead at QuantX.
Thanks, Sarah, and good morning, everyone. So maybe for a little bit of a change of pace, in terms of the research and development for impact, I thought I'd give you a bit of a case study on what we've been working on, and a bit of a slideshow at the same time. We're maybe not as developed as some of the other speakers, and so we're still on this journey. And I think we've made a bit of a few learnings on the way. So first of all, this project that I'll talk about is supported by Moon to Mars demonstrator mission by the ASA, and has been developed inside our Space Photonics production facility that's also been supported by the ASA's Supply Chain Capability Program. So our goal is to demonstrate QuantX Lab's tempo optical atomic clock in a low swap satellite payload for on-orbit timing. Our terrestrial clock is on the order of 100 litres, 50 kilos and 200 watts, so that's pretty large for a satellite platform. And so our goal is to reduce that swap in the fastest possible way to demonstrate that technology and show its value in space. That aims to shrink it down to payload on the order of 20 litres, 20 kilos, but still with a relatively high power consumption of 100 watts. And then from there, once we've demonstrated this, the value of this technology, then put further investment into it to shrink it down to the ultimate potential that can be achieved with optical timing systems. So you might ask, why are we interested in space clocks? Firstly, there's the obvious application on Earth, where GPS utilizes clocks in space to provide navigation and timing services for across society that has significant impact on commercial value on Earth. Furthermore, there's a need for on-orbit timing services for satellites, including synthetic aperture radar systems. And then going a little bit beyond the Earth, systems like the proposed lunar net will benefit from high-precision optical atomic clocks or similar type technologies to provide services to the moon. And then further away from Earth, as you go into deep space, high-performance clocks can provide reduced reliance on Earth and enable deep space navigation, where the cost of taking out payloads to very far away from Earth is very high, so shrinking down the size and weight of these systems is vitally important. So how do lasers make better atomic clocks? And how do these systems work? First, you choose a property of an atom that is unchanging. This is the orbital electron structure of an atom, and you choose a transition that you can access with a laser. So this is an intrinsic property of the atom, and these properties are the same across the Earth and the universe, nominally. Then you interrogate that transition with a stable laser, and you tell that laser to track the energy level of your atom. This means you now have a very stable laser that will produce the same timing signal no matter where it is in Earth or in space. However, you have a problem. Having a stable laser doesn't enable your electronic systems to use that timing signal. So there's a key enabling technology called a frequency comb. This is a kind of pulsed laser that allows you to translate stability from optical frequencies into RF systems. From there, you can use that as a readout for your system, connect it into your satellite or your telecommunications system. So how are we going about this process? There's two payloads that we're interested in as a part of this program. One is a Pathfinder mission based on this optical frequency comb technology. We'd like to show that this technology will work in space, and by doing that, we can enable the future use of optical atomic clocks in this environment. This also provides us a pathway to develop our own space heritage at QuantX Labs. This is our first space project, so it's quite ambitious. And will also provide vital information on the satellite interface that we would like to use for our future demonstration of optical atomic clocks. The second payload that we're interested in is the optical atomic clock itself. This will be a high-performance timing reference with low size, weight, and power. We really want to demonstrate the feasibility of this technology in space, as there are a lot of unknowns about using these photonic systems and atomic interrogation in space. And at the same time as doing all of this, we need to engineer this terrestrial system for the challenging low Earth orbit environment, which can involve obviously vacuum rather than air, but also radiation and then thermal interfaces of, say, 70 degrees, or 70-degree changes. So this is quite an ambitious program, and because of this, we've taken the approach that we want to develop the technology and test it rapidly over multiple times. So starting with engineering model prototype that was supported by SmartSat CRC, we're developing a qualification model of our comb payload, then a flight model, technically probably a proto-flight model as we're incorporating the learnings of our development. Then once we've kind of developed this technology and demonstrated it, taken the learnings from this process, we're developing the clock payload qualification model, and then finally the flight model of the clock to provide our demonstration. So a fair amount of effort went into the design and engineering of the systems, but I'll just show you some of the highlights. Once the frequency comb payload was developed, we took it out to the thermal vacuum chamber at DST, which we appreciate the support of Chris Peck and his team. We then tested it across this operational temperature range of -10 to +50 degrees, and found that all of our thermal designs and thermal controls are working. Then we took it out to APC Technologies, a testing company here in Adelaide, and shook it to simulate those launch vibrations. And then finally, we took the core electronic subsystems of our clock and our photonic systems, the frequency comb laser, and exposed that to simulated radiation to determine the survivability of all of those systems to the radiation on orbit. And here you can see some of our engineers, Sid and Enzo, out at the Melbourne Synchrotron. By doing this, we then understood that the changes to this technology we had made enabled it to operate in that environment, but there's still, I guess, a challenge, equally significant challenge ahead, which was making sure it works with the satellite that the payload needs to be integrated into. So our launch service provider in this case is Exatrail. They're a rideshare company with a satellite called SpaceVan over in France. And so again, some of our engineers took our engineering model and plugged it into their satellite and made sure that the software and electronic interfaces could mesh with the satellite, and we could have all of the functions of our payload that we're expecting. This was really a big kind of tick for us to say, okay, we've gone through the steps of this development, we've kind of engaged in the space industry, and we're starting to see that our plans are coming to fruition. And so that completed the testing of our qualification model. From here, we started working on our comb payload flight model. This incorporated some remedial work, so it maintained consistency with our clock payload, because we are really keen on matching the ICD, or interface control documents, between our two payload systems. We then again took this system out to APC Technologies to shake it, and we're very lucky to be able to use Fleet Space's state-of-the-art TVAC system, really, really nice piece of kit, to do our thermal vacuum testing. From here, we've done a whole bunch of in-house testing, and then we've packed this up, shipped it over to Exatrail, and this is to their their satellite integration facility in Massy, one of the suburbs of Paris. And now it's been bolted on board their Space Van 002. And so on the right, you can see the gold MLI surrounded by the radiators which will enable the correct thermal environment for our payload interface. So that's now been integrated onto the satellite, and we're scheduled for launch at the end of this year. I think December is the plan via SpaceX. That still requires the space van being shipped over to Texas, so fingers crossed on that one. From here, this kind of taught us a lot about the method of taking this kind of photonic technology, going through the engineering process, and then also navigating the somewhat challenging kind of environment to get your satellite bolted into a launch service provider's satellite. So we used these learnings and started the development of our qualification model for our full optical atomic clock. So here, this required a kind of ground-up redesign from the engineering model that was supported by SmartSat CSC. A lot of the focus is on fine-tuning the kind of thermal transfer needed to meet on the order of 1 millikelvin temperature stability in our atomic interrogation payload with an interface that can vary by 70 degrees. And then also addressing a bunch of the kind of AIT learnings that we had along the way for the sim. And then continuing the kind of, these optical atomic clocks require quite complex control systems. And so fine-tuning the software and firmware to enable precision locking of your lasers to your atoms and temperature control. This was then tested in our photonics assembly lab in Lot 14. Again, we shook the heck out of it at APC Technologies, and we also did component level, subsystem, and system level vacuum testing at QuantX, including performance testing, and then qualification level thermal vacuum testing out at DST. This revealed to us some issues. So this testing showed us that some of the components that we'd taken from suppliers and taken at face value, the kind of specifications that they should be able to survive wasn't quite right. And so we found that there were some failures in particularly our photonic components. So to mitigate this, we then identified the cause of each of those failures, did component level testing and vibration on the individual components, found where they were actually likely to fail, and then we incorporated those design changes into I guess, like component level or subsystem level designs that we could test, and then we shook the heck out of them and made sure they survived. This kind of completed the qualification model, and it's just up to the flight model now, which is a process that we're currently underway. So we're taking the outcomes of that qualification model design, incorporating the learnings from all of our testing, both our our comb payload and clock qualification model, and we've redesigned the entire system based on those learnings. We've passed our production readiness review, and the build is currently underway as we speak. I think we're about a month into the process, so fingers crossed for that. And we have a target for the launch late next year. So I think I just wanted to give you an idea on the kind of rapid approach, and that's why I spoke rapidly, it's for no other reason. The rapid approach we went through to kind of take this really research output from the University of Adelaide and then rapidly iterate through cycles to retire technical risks, and also improve our understanding of the space industry as well. While we're yet to see the outputs of this, we're very hopeful, but I'd just quickly like to speak about the impact it's had on the company as well. In addition to the other products that we're developing, our cryo system for the over-the-horizon radar type systems, the terrestrial arm of our clocks, laser timing sync, resilient timing networks, and our quantum magnetometers. Over this period of the project that I've described, we've doubled the size of our company from around 20 people to 40 people. And we've reached the point where we think that we've shown enough value that to continue this growth, we're seeking capital investment to expand our company again, at least double in size. So I'm very grateful to the Australian Space Agency and SmartSat on the support they've given us, which has enabled this kind of pilot demonstrations of our technology. Of course, all of the support that we've had from DST and Defence and our partners at the University of Adelaide. And I'd say in this process, also the kind of Australian space community has really supported us. So we've got a great independent review panel with a lot of valuable experience. We've had really good collaborations for access to facilities and testing with some of the other Australian kind of space companies, and always a friendly ear when we're asking, okay, we need to deal with this supply chain issue. Who has a bag of MLI in their back cupboard? Can anyone help us out? And people have been really supportive. So I hope that kind of gave you an insight into the process that we've gone through, at least, to kind of take this emerging technology and then rapidly carry it through to something that we think can produce a lot of value to Australia and the world. Thanks a lot.
Okay, last but not least, we have Byron, who's a partner at Deloitte. So Deloitte's global space business includes around about 600 practitioners, many space systems engineers, and they serve a diverse range of clients across the sector: defence, civil, government, etc. What's not known to many, though, is that Deloitte is not just a space advisory business, it's a space business in its own right. And Byron's going to be talking a little bit about that. And relevant for today's discussion, a little bit about Byron, is that he serves on the US headquartered board of Space Information Analysis Sharing Centre, and he was actually the first non-US board member of that committee. So Byron.
Thanks, Sarah. That was a very indulgent introduction, but thank you. Good morning, folks. Space is indeed a team sport, and I'd like to share with you an initiative of the globally aligned Deloitte Space team, the team that Sarah has just mentioned. And this relates to a platform that we call Deloitte Silent Shield, which is a defensive cyber operations payload for satellites, providing on-orbit real-time anomaly detection and threat visibility. So in today's landscape, particularly the defence landscape, reliance on satellites is clearly more critical than ever. Satellites play a key role, a vital role, as you know, in secure comms, enabling precision navigation, guided weapons and surveillance. As space-based assets and cyber vulnerabilities increase, protecting these assets becomes crucial for national security and for cooperation with our allies. And in the words of the commander of the US Space Command, General Stephen Whiting, cyber security is the soft underbelly of space operations. And without the cyber domain, there are no space operations, no communications, no ground control. And the next great threat to our nations will likely come in the form of a cyber attack in, from or through space. And to bring this into stark reality, a situation that many of you would be aware of, but it just brings it to life. It was less than 3 years ago when a cyber attack on Viasat's KA-SAT crippled Ukraine's military operations and paralysed the civilian comms across Europe. And it was only yesterday here we had Major General Samuel Keener, and as well as Major General John Olson, who's presenting at the same time as me right now, but reminded us of the rapidly growing threat vectors affecting space assets, arising from the increasingly congested, contested, and highly competitive space domain, especially the efforts from China and Russia. So there is a compelling need for secure space systems that we can trust. Silent Shield, our platform, is the first on-board cyber defence platform providing in-orbit threat detection and real-time responses. To just give you a little bit more colour on this, I will just play a short video.
It's not just for Earth anymore. Thousands of satellites are carrying data around our planet, and 100 terabytes of data are sent to and from space every single day. Malicious actors already understand the significant value of attacking space assets and holding data for ransom. What's protecting our data as it orbits our world?
2, 1, ignition. Liftoff of the Falcon 9. Go SpaceX, go 13. Deloitte 1, deploy confirmed.
Introducing Deloitte's Silent Shield, designed as an out-of-band defensive cyber operations, on-orbit solution, vehicle anomaly detection, and predictive analytics via AI and ML. Now it's possible, providing space operators with near real-time predictive cyber analytics and risk detection. Seeking cyber resiliency in your space operations? Contact us for a demo today.
So, Deloitte 1 represented the release of this Silent Shield platform, an R&D initiative of Deloitte. It was launched on Transporter 13 in March. But from a defence context, no other defence force has this particular capability. Silent Shield is defining new cyber standards. I might speak to the cyber standards piece on the panel in a moment. So our view is that this capability is at least 2, maybe 3 years ahead of alternatives that are still in early R&D. It operates covertly, making it difficult for adversaries to detect it. And by tracking every known anomaly on a satellite, Silent Shield strengthens Defence Force's ability to address vulnerabilities and mount effective responses to future threats. It's also innovative in a number of ways, but one way is through its out-of-band comms port, allowing communications that delivers threat detection that avoids interference with the core comms on the satellite. It's also differentiated by its high level of feasibility. I think this will be an interesting sort of debate point in the R&D session today, where we contemplate technology readiness levels. But you saw that this capability was launched on Deloitte 1 via Transporter 13, very close to TRL level 9 now. Deloitte 1 represents the first in a constellation of 9 Deloitte space assets planned for orbit over the next 18 months, designed to enable innovation, training, test and space-based data insights. But with its modular design, it can be integrated now for rapid scale and deployment. And so I'd be interested in conversation with a number of you who have space missions planned in the near term. There is a question, of course, about how are the insights that are generated from Silent Shield, how does that occur? Silent Shield has been designed to integrate with another Deloitte platform, another R&D initiative, Deloitte's leading complex systems decision support platform, a platform that we call Optimal Reality, whose development team, in fact, a number of them have been on the Deloitte booth here at the Space Forum. So Silent Shield, combined with this Optimal Reality data AI simulation engine, provides real-time recommendations and learnings from each incident to adapt and strengthen a satellite's performance and its defences. What I'll do is share play another short video that introduces the Optimal Reality platform. This is a platform that we've now adapted for the space context, but I'll just give you a bit of colour on how it's already being used in commercial applications today.
More decisions will be made today than on any other day in human history. And these calls will make or break tomorrow. That's why at Deloitte, we've developed software that can simulate the real world to master trial and error, without the error. We call this Optimal Reality. OR lets us create digital twins of the biggest systems in the world around us, like transport, energy, and emergency response, where we can explore different futures until we find the one that's best in real time. Before we make any important decision, OR has seen and tested millions of outcomes, delivering better productivity, less risk, more efficiency, and faster problem solving. Based on world-leading simulation and AI techniques, OR has helped create one of the world's most advanced intelligent network management systems, solving complex aviation problems in some of the world's busiest air routes, reducing waste, emissions, delays, and frustration. On the ground, we've partnered with one of Australia's largest road network control centres, deploying a real-time digital twin of an entire state's road network, enhancing the daily commute for millions by analysing 500 million data updates each day that inform critical decisions made on the network. Beyond transport, OR extends to solve a number of challenges in a variety of industries, providing the data needed when it's needed for safe, ethical, and effective autonomous mission control, truly providing an optimal reality.
So that particular platform, if you travelled here on an aircraft, almost certainly would have affected the flight planning that went into your trip to come to Adelaide. It's been used by Air Service Australia. You've also heard reference to one of our major transport networks here in Australia. But optimal reality has now been augmented for the space domain, and so it's sort of like the yin and the yang, the two parts of this presentation, the silent shield, anomaly detection and cyber capability for space assets on orbit, combined with this optimal reality engine, are the way that the insights are coming from this platform. It also gives us the ability to turn this capability into a training platform. And so in the spirit of Talisman Sabre occurring at the moment, it provides an excellent operations, training and testing collaboration platform for space operations. So Silent Shield and Optimal Reality together present a game-changing opportunity for a number in the Australian context, but particularly defence, for those looking to bring trust to space-enabled operations. And I look forward to sharing a little bit more about this, but exploring the partnership opportunities of this capability with you through the panel just now. Thank you.
All right, so I do want this to be a conversation. The panel members have been instructed to jump in if they have something to offer in the questions. I've got a few that I'm going to start with, but there's going to be some roving mics around. I actually can't see anything out there, so you'll just need to get the attention of whoever's walking around with the roving mic in order to be heard, or jump up and wave or flash your lights or something like that. Okay, so I'm going to start with one for you, Kim, actually. So that was probably one of the better presentations I've seen out of CSIRO, because there was a lot there that I wasn't aware that CSIRO were doing, and it's quite an impressive portfolio of technology. But what are the key barriers in getting that R&D, which clearly has impact, getting it into a commercial valuable product? What are those key barriers?
So I think the first barrier that we are trying to address in assisting the industry is really around raising the TRL level. For things that we want to send into space, even if we think that it has excuse me, great commercial potential, typically around TRL 7 is about the earliest that a potential commercial partner or investor would really take it seriously. So obviously there's quite a high cost associated with achieving getting things into space. So certainly with our space technology program, that is where we have tried to help make a difference to overcome that big challenge and get to a point where industry can benefit from it without having to make that massive investment themselves. Other challenges I would say are around scale. So turning something from a laboratory demonstrator type activity to something that's actually of commercial scale. I sort of mentioned that or touched on it with our solar panel development, for example, where one of the key considerations we've been looking at as we develop that is how do we actually produce something that can be made at a commercial scale rather than just a laboratory scale, because there is a lot of research going on in that field at the moment, but most of it is constrained to laboratory scale, which is not readily manufacturable. And then probably the third thing that I would mention is around market access as well. And so obviously we have a fairly small market here in Australia just by virtue of the small size of our country, and space is very much a global enterprise, but how do we get into those international supply chains?
Did anyone else want to add anything? I've certainly got comments, but I'll let you guys go first.
Yeah, I just want to add to, I totally agree with everything you've said and definitely echo that. But one other thing that we've noticed is by virtue of being a space company, you're automatically competing internationally, but then getting into the international supply chain is a real barrier as well. So it kind of works both ways, really.
Do you not have a mic? He's sitting on it.
Sorry, I didn't even find my mic. I sat on my mic. I just thought I'd pick up on that, or this international challenge aspect of the question. Probably two aspects. In relation to that particular sort of platform that I was pitching, this has been developed by Deloitte globally, input from Australia, US, etc. But we have defined gaps in our platform roadmap where we're going. And so we are identifying capability here in Australia that we'd like to bring into that. So great capability and input into a platform can come from anywhere. So we're looking for the best. So there's a comment around Go Australia there. I think the second, and that's go many in this audience, because we'd like to have a conversation, but back on the point of access to markets, I think this is a really good debate. Some of you may be aware, and this I want to go outside of that Deloitte platform I pitched, but Deloitte struck a partnership with iLaunch, the space trailblazer. So they're doing some fantastic projects, capabilities here in Australia, but they're not pursuing, or we're having difficulties getting access to international customers. So here is Deloitte, extremely privileged with clients all over the world, privileged access at board level, exec level, and in the key markets where space capability is relevant. So it's been a privilege to partner with iLaunch to help them access international markets where these conversations are built on trust. It's not like we're just knocking on doors of organisations we met yesterday at a conference. These are, I think of some of the openings in Japan. These have been forged on relationships that go back decades. So I think there's a question around how we access international markets. There are definitely needs. So I think there's a conversation around who you talk to and how we get there, and work, particularly with trusted networks. So that would be my comment to this challenge. And we've got a precedent that's working here in Australia at the moment.
So, from my perspective, certainly that de-risking, industry, particularly in a sector within Australia, it really is hard to kind of understand where the sector as a whole is trying to go, and that high-level strategic planning, and that does make it incredibly difficult for industry to go, yep, I'm going to pick that up, because I know at the end of it there's going to be this mission or that mission or this capability. But in terms of that global footprint, particularly for I'll say the startups or the small companies, where you know that this is a global product that you've got that, from what I've seen, everybody should be wanting to pick up. Not having that ability to go and set up an office overseas, or, have, someone in Europe and Japan and the US, how do you go about overcoming those challenges of getting that R&D outside of just Lot 14 or just Cicada or just, Australia?
Sure. So I think there's a range of programs that we use to send, personnel from the company around the world to talk to relevant customers. And I think, at least for us, we're in maybe a niche market where precision timing has like a handful of players, and so you can just go and talk to each of them, find out where the opportunities are, and build strong relationships with them. I think there's also an element in, I guess I talked about what I saw as that initial demonstration of technology showing the value, but there's a second element of that which I think that maybe is something that we can all improve on, which is, at least speaking for ourselves, our small company means we may not have the access to relevant stakeholders and customers, especially even within Australia, that some of the larger organisations do. And so support on that end of the spectrum is also very important to us. So not just the funding that can incentivise the original research and development, but also the support in getting that, once it's demonstrated, into customers' hands, making the connections to the right people is really critical for us.
That, I think you said it, and the commercial readiness levels. So you've got your technology readiness levels, one thing, but being commercially ready. But did you want to add something to that?
Yeah, I was just going to say, one thing we've had a lot of, I guess, traction with is partnerships internationally. But it is tricky, right? Because getting to that higher commercial readiness level with a company that's big enough and got enough money behind it to do that is also really tricky. So we found that partnerships and collaborations with smaller companies that are really technically competent, they get our stuff and they see the value, but then articulating that to other people is sometimes hard. So that's kind of what we've been doing, but also I guess a challenge there as well.
Yeah, and I guess the common theme of that is that trust. It's that building that relationship so you can go in, you can share IP, so then they understand the value of it, and then building that trust, like you said, Byron. All right, the next question I have is around test beds, demonstrators and pilots, and that's part of that, raising that TRL from that TRL 7, like you say, Kim, is, getting it out into the lab, developing it in the lab's one thing, brilliant, love it. Getting it out of the lab and breaking through that TRL 7 barrier is incredibly difficult and expensive. So my question is, and I actually want to start with you, Seb, because you've gone through a very traditional, albeit aggressive process of that systems engineering. You start with your engineering model, your pre-flight, your blah, 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 blah. How does that compare to trying to use or go straight to a prototype and, the Elon Musk, fast fail? If it doesn't work, we'll just keep iterating on the final product rather than working through those test beds, prototypes and that system. So can you elaborate on why you chose to go through that systematic? I'm a systems engineer, so I'm fully supportive of your process, as opposed to just going, wham, here it is, let's get it out, and then try and figure out if it fails, why it fails, and that fast fail approach.
So I think part of it for us is the restrictions on the technology itself. It's quite a complicated instrument, and so I think it would be quite arrogant of us to presume that if we just took the way we imagined it would work and implemented it, that is, in my view, unlikely to work. I think maybe although we're nominally a traditional approach, we are much faster, and that means that we do have to make concessions similar to the alternative approach. So we may not have a full amount of information before we start the next cycle, but the goal is to test everything we do and test it as quickly as we possibly can. And so it's really about, instead of having your traditional engineering model, building it, testing it fully, doing that full analysis, identifying all of the risks and making sure throughout the program of work that every one of those risks has been mitigated or understood. And so I think doing that in one shot for us was just not feasible, and especially as a company that is just putting its toes into the space industry, the engineering challenges are pretty significant, but I guess the higher level challenges in forming those relationships with partners and getting the contracts in place to bolt our hardware into people's satellites, that's equally challenging. And I think having that step-by-step approach taught us a lot along the way.
Yeah, can I just add to that? So I really liked your presentation, how you sort of were saying, these are the steps that we took, this is the learnings we had, this didn't work, because not many people in the industry do that. There's not a lot of transparency about this broke, and this is why. And we see this at Deneb Space. We see companies making the same mistakes, and we're like, we're on the bench, guys. We have the tech to help you, like, sub us in. And it's really frustrating to watch that. And I think the reason, though, that we've got that kind of knowledge is that systems level engineering approach, and being like, there's this hardware software integration that we have across all of our tech that allows us to have that kind of overview and identify these knowledge gaps that big, well-established companies are making really silly mistakes, and they won't admit to that, which is fine. I mean, no one wants to be that person, but taking that step back, looking at the testing, the systems engineering is so important, and that's how everyone is going to succeed.
I would maybe add to that, although I appreciate that maybe the compliment, we have a hardcore independent review panel for our project, and they keep us honest, so that really helps on those sides of things.
Which is important, and not everyone does that, so, you know, like, that's awesome as well.
And I think the good thing about the space sector, I'm on a couple panels, is that everyone's so passionate about seeing these things get into space that it's actually, I don't know what your experiences are, but I love being on those panels, you know, volunteer on them and try and provide that expertise in. So I think if you're developing a system or a program or something and you don't have an expert panel from the sector, then put your hand up, because there's so many people out there that are happy to put in, I don't know, 2 hours a quarter or whatever it is to read what you're doing and really help accelerate that the success of what you're doing.
I might just add too, in addition to everything that's already been said, just highlighting that CSIRO does have a number of facilities, test beds and so on that are available for use by the industry. And so obviously, you know, the various testing facilities that you need can be quite expensive. You don't want to have to buy every single one of them yourself or anything like that. So there are facilities out there nationally that can be leveraged to assist with that as well.
I think I'm going to jump in on this one too. So there was a great example there from Seb around distributed testing effectively, right? So just switching hats, you heard reference in the intro that I sit on the board of the Space ISAC, which is the US headquartered Information Sharing and Analysis Centre. They're an industry group, not-for-profit, that's all about resilience in the whole life cycle of space R&D to operations. One of the programs that they've got at the moment is what they call ASC 100, but it's a joined up initiative with Aerospace Corp and the Space ISAC. And it's all about test beds and proving grounds. And the point I want to make here is we've got a problem in the sector. We've heard a number of presentations from Defence yesterday, particularly John Olsen and others, around urgency and agility. So there are currently bottlenecks at the moment where US space companies can't get their stuff tested quick enough. So Aerospace Corp and the ISAC were challenged by the US Department of Defence. What can we do about this? And so they want to disrupt. They want to still keep the structure and the discipline, but doing it the slow, sequential way isn't going to get us where we need to get quick enough. So there's a dilemma here. So my encouragement to close this one out, for the research organisations here and those with great testing facilities, I would encourage you to look up the Space ISAC and that particular program. That they are effectively going to be connecting demand and supply. We have one Australian organisation, so the iLaunch have signed up to it. There's already an example of a US hypersonics company who's bottlenecked, and so they're going to look to do stuff here. So I think I would encourage you to sort of look at the disruption that might be occurring here, and I think, Anne, for you, I'd get involved, because some of those guys in that group would be your customers.
All right, I've just realised we've only got 3 minutes left. So I'm going to open it up to the floor for questions. So you're going to have to make some noise so I can see, at least generally trying to figure out where you're at. If there's any questions, I'm assuming there's a roaming mic. Oh, the mic has a roaming mic. Yep. Any questions? I heard a yep. Oh, up in the stand. Thanks, Mike.
Thank you. Yes. When you're doing R&D for innovation, I think you're often involved in a tech push. And I think, Anne, you've got some non-traditional solutions to existing problems. How do you deal with convincing the people with the problems that actually this non-traditional solution that's coming out of this R&D is something they should consider?
That's a very good question. So we take the engineering approach of the numbers speak for themselves. So for example, our magna torque, I'm like 10 times the amount of rotational torque. Do you know how much that is for a satellite, how agile that is? And then starting to talk through that conversation, or saying, what could you do with 50% extra power budget? Imagine the better payload you could put on board, or not having the burden of having to have this other constraint. And then having those conversations, people are like, oh, okay, I get it. So I think for us, we've been really lucky that having valid numbers really supports our argument, and we kind of just present that and then let the people run wild with that is basically what we do. I will say though, particularly around like the AI in space piece, a lot of people sort of tend to be risk averse, but once again, demonstrating it in a systems test bed that we've heard about and the importance of that, and validating that and showing, okay, what's your concern? We've already tested that. We've tested this scenario, this one, this one, this one. Really adds credibility to what we're saying as well. So that's how we approach that.
Yeah, thank you. Yeah, I think people love deterministic systems, and yeah, when you're adding AI in the mix, I think you have I guess a higher burden maybe to show people that it actually works. So yeah, you can show it in space, but maybe show it 10 times before people actually go, okay, yeah, that seems to make sense. Yeah, thank you.
Good question. All right, we've got time for one more question.
I'm just the mic runner, but if there's no other questions, I have a quick one for Kim, and it's about algal blooms, which is quite a serious environmental problem we've got right here in South Australia. Has the South Australian government asked you for any help?
I'm actually not the right person to answer that, but Alex Held is sitting right there,
okay.
and he might have something to add. Alex is our Chief Scientist for Earth Observation and Aquawatch at CSIRO.
Thanks, Kimberley. Yes, we have had a couple of our scientists already at some of the key meetings here with the state government. In fact, right at this moment, there is a special meeting again with, I think, 2 ministers of the state government attending some of these technical meetings. So, and we know we can see it from space. That's no problem. It's big enough. I guess the trick we want to develop into Aquawatch is actually do the spectroscopy of the bloom, so we know what species of phytoplankton it is, not just that it's green. So yeah, that's the plan. Thanks.
And Michael and Alex, I'm going to quickly jump on that. Deloitte has got a wonderful partnership with CSIRO at the moment on the Aquawatch program. But for those of you that are interested, there's a program that we're running called Gravity, the Gravity Challenge. So we've got an Aquawatch edition, under Gravity 08. So what we've done is exposing this great platform to a number of demand-side use cases, like the one that Michael's described. So there's a fantastic problem set from Melbourne Water, for example, at the moment, into that program, and there's some UK challenge as well. So for the innovators in this audience, I would encourage you to hop onto the gravitychallenge.space website, because you could participate kind of directionally in that issue that Michael's raised. But we should have those conversations, Alex, with the SA government too.
Yep.
All right, on that note, I don't want to be responsible between you and morning tea and your next coffee. So if you join me in thanking the panel members, then we'll go to morning tea.